Good morning. During the last lectures we have dealt with the construction of the towers and the beams of cable-stayed bridges. Today we will deal with the installation of the stay cables. This merits a lecture by itself because it's the one particular construction and a structural system for cable-stayed bridges. You hopefully remember two lectures in the last semester where I lined out the different types of stay cables, their makeup and fabrication and so on, and we will come back to these different types now. We have the locked coil ropes and the parallel wire cables, both of them shop fabricated, so they come as a complete unit to site and are installed as a complete unit. Contrary to that, we have the more modern, mostly used today type, the parallel strand cables. Now, they come onto site in components and are built up from their individual components on site. A very brief note on cable calculations. They are given in all sorts of handbooks. We don't need to do much there. Now, locked coil ropes. Just to refresh your memory, locked coil ropes consist of outer three layers, typically of Z-shaped wires, and there are round wires inside. Now, the outside Z-shaped wires are helically wound, and if we pull at them, they lock into one another and produce a closed surface which doesn't leave in any water, so they are just painted there. They are, as I say, completely shop fabricated, and they are transported to site on reels with a considerable weight if they are long and thick. And they are stressed basically by a hydraulic jack, and the connection between the hydraulic jack and the anchor head is done with a pull rod or tension rod, which is screwed into the anchor head and is screwed into the hydraulic jack, and in between there's a support nut. So we pull, the support nut is forwarded, then the cable rests on the pull rod and support nut, the jack is retracted, and so on. So it goes in steps of something like 25 centimeters. As an example, we use the Niederwarter bridge, which is very close to us here, you may know. The cable anchorages at the tower head for the Niederwarter bridge are composite anchorages, which means it's basically a steel box into which the cables are anchored, and then the box is cast into concrete. We see here the details. We have the cable, we have the anchor head, and there are some crossbars underneath the anchor head to prevent that the cable runs away here. The same here. So it's anchorage in steel. At the beam, similar. We have a composite beam, and the stay cables are anchored to the steel girder grid on some short cantilevers. We see it here in detail. There's a bracket, and we have a steel pipe also welded to the steel bracket. The cable is introduced and is supported here, in this case, by a support nut. In detail, the anchor head at the top of the tower is a so-called hammerhead anchorage, we see obviously why it's called a hammerhead anchorage. And looks like this. The steel wires are cast into this in a conical opening with hot tarmac zinc alloy. Now, the installation goes on that we pull up the cable to the what we may call passive anchorage, which is the anchorage where we do not stress. And we support the rope, in this case by 2 crawler cranes, so that the sag doesn't become too big. It's pulled up and installed in the tower head, and then the actual stressing at the beam end starts. We see here the overall picture. We have here the anchor head. The anchor head at the bottom is cylindrical, not a hammerhead. And then we have screwed this tensioning rod into the anchor head, and the tensioning rod continues to the hydraulic jack, which stands on a jack chair. We can see it here more in detail. This is where the cable comes down. This is the anchor head with an outside thread on which runs a support nut. The tie rod is screwed into and runs through to the hydraulic jack underneath there. And here we see now the bottom end. We see the tensioning rod coming through here. There's the jack behind, and here we have placed the support nut. So once with the tensioning rod we get the anchor head of the stay cable through the anchorage, then the support nut is screwed onto this outside thread, and the length can be regulated by varying the position of the support nut. That's basically the installation of the completely shop fabricated locked coil ropes. Now we come to the next, the parallel wire cables. Because they are also completely shop fabricated, there is some similarity in the installation. They also come on reels, and then they are rolled from the reel on some small movable carriages. Now, the parallel wire cables are, as you may recall, they consist of parallel wires in a PE pipe. Formerly, the PE pipe was empty. We will see later an example, and cement grout was injected. Today, very often, there is some petroleum wax already inserted into the PE duct in shop, so there is no additional corrosion protection necessary. However, this PE polyethylene pipe is a little sensitive, a little bit more sensitive than the steel-only lock coil ropes. Therefore, we have to be a little bit more careful when installing. That's why we, first of all, lay it out on some movable carriages. We must always be very careful not to bend it too strongly, then it may burst. And then here we install a tensioning rod, and we lift up first and then to the tower head, in this case also the passive anchorage. We have here sort of not really a spreader bar which distributes the supports, but at least we have 2 supports with which we try to ascertain not to have a too sharp bend in the PE pipe, which would take place if we supported only at one single place. That's why we use 2 supports here. And so it's pulled up from the deck, and the pull cable with which we pull it up, we can see here runs through the anchorage in the tower head. Again, it's a steel pipe cast, in this case, into the concrete. It's pulled through. We see here the next cable is already in. And now we are inside the tower head. Inside the tower head is correct. And we see here the cable anchor head being pulled through the steel pipe. And then two shims are inserted here. You can see, if you look very closely, there's a joint between. These are two half shims with a hole in the middle, and they are moved inside so they support the anchor head. It can't slip through anymore. So the passive anchorage here is installed. Now we come to the active, meaning stressing anchorage at the beam. Again, similar, we have here the anchor head. We have the tensioning rod screwed into it. And at the end of the tensioning rod, we have one or two strands with which we pull, first of all, the tensioning rod close to the hydraulic jack underneath. So this is then the situation underneath. The tensioning rod has been pulled so far that it can be installed with a hydraulic jack. The hydraulic jack again stands on a jack chair, because this is the place where finally the cable anchor head will locate it. And at the end, again, we have here the anchor head, and we have two shims put in between to keep it in place. We can vary the length of the stay cable by varying the thickness of the shims. In certain bridges, we just define for the construction manual the thickness of shims for cable length, because it's difficult to measure the full cable length on site, but you can very easily measure the shim thickness. So the shim thickness defines finally the actual cable length and forces. Now, completely different installation method is with the parallel strand cables, not shop fabricated, but they come on site in their individual elements. Of course, all the fabricators are in competition. The fabricators are, for lock coil ropes, Bryden, Thyssen rope it was, and they have been taken over by Bryden. So they are the only ones that I know of which still fabricate lock coil ropes. And then all the others produce parallel wire cables as well as strand cables. They are DSI, Dückhoff and Wittmann. In Germany, VSL, Vorspannsystem Losinger. In Switzerland, there is, in Japan, Shinko. There are Chinese fabricators of parallel wire cables. The name I don't know, but I've been on their site, and some others. And so there's a competition, and the competition is by price, because we can design a cable stay bridge with parallel wire, parallel strand cables, and so they offer to the contractor their price, and the contractor normally chooses the most effective. So it has evolved on site over the years that the parallel strand cables, with their construction from elements, proved to be the most economic. And even in Germany, where all the early cable stay bridges used locked coil ropes, now we have the last two with parallel strand cables, which is Rheinbridge Wesel and the Strelasund Bridge to Rügen, which we have mentioned. So this is their sales talk. I'm just giving you as an example for the competition. So for parallel strand cables, it is claimed they have reduced construction loads. Okay, they don't have the full heavy weight. Therefore, greater mobility of the installation equipment because it's individual components. Naturally, if you do it piece by piece, you repeat the operation very often. Greater flexibility because from components. Capacity of adjustment to structure geometry, I think that's true for all of them. Independent operations, yes, and they claim, that's an important thing, easier maintenance and repair. The parallel strand fabricators claim they can exchange any individual strand and replace it, because it's just reversing the construction method. And that, of course, is important. If we have corrosion, we do not need to replace the complete cable. We can replace individual strands. How much that really comes true in 20 years on site, I'm not sure, but theoretically it's possible. So, the strands are supplied just by themselves on reels. The PE pipes around are also brought separately to site. There's a scaffolding, of course, to be built around the tower for installation work. And we start the installation of parallel strand cables by placing the passive anchorage, just the anchor head by itself. In this case, again, the passive is at the tower head. Normally we stress at the beam. There are special cases where we stress at the tower head, but we need more space and so on, so we'd rather do it on ground. So, first of all, we install the anchor heads, which have these holes through which the individual strands are threaded, and then they are connected with wedges. You may recall I showed you these are small steel wedges with threads, and they can be very strongly pre-set or set with a hydraulic check, and that's their way of anchoring. I told you all that before in the last semester. Now, then we start making one long PE pipe from the individual sections. It's arranged on site, and then here we see two ends of a PE pipe, and then we use the butt welding or fusion welding, which means there is a hot disc inserted between, then the two pipes are pushed against the hot disc, they melt, the disc is taken out, and bang, they are pushed together. And the result is a butt weld, which is as strong as the PE pipe itself. That means once we pull at a test PE pipe with a weld in the middle, the pipe should not fail in the weld, but somewhere left or right. So we have now welded together the long PE pipe. Now we have to lift it up. Remember, there is no anchor head at the top now to stiffen the pipe and so on. So we need some temporary attachment to pull it up. And this, therefore, some sort of a collar is used. There's some stiffening mechanism screwed on, and this collar is also, so that's all temporary, to lift the pipe, which basically is empty. It's just the empty PE pipe. So we can see it here. We lift it off the reels. That's the tip. This is the pull cable attached to a winch. Take it up. And here we see already the first strand is placed, but there's no tension on, so we lift up the head. We have then a very big sag, of course, because there's nothing, it's just the PE pipe, and we cannot pull very much on the PE pipe. Big sag. And then the first strand, which was already inserted during lift, is stressed. The first strand is attached to the final anchor head at the top, which I showed you. Here. See, it's inserted here through one of the holes, wedged, and then we can start pulling at it at the bottom, and with this strand we can then take out most of the sag, and the cable becomes more and more straight. Now we then have to install one strand after the other, always in the same cycle. I just line it out and then show you the pictures. We have an instrument here called the shuttle. Now you are probably all aware of a shuttle bus, for example, which runs permanently between two end locations, and this shuttle runs always up from the bottom to the top and back. That's why it's called a shuttle. Then we pull the new strand up. We have to introduce the new strand into the top anchorage, which I showed you. Then, because it's a long strand from a reel, we have to cut it at the bottom. Then we introduce it into the bottom anchorage. And then we make this isotensioning. Now, isotensioning means that although we install one strand after another, and by pulling at every new strand, the already installed strands naturally lose a little bit of their initial stress. Now, how do we end up with all the strands having the same desired stress? It's fairly easy. What we do is we overstress the first strand. Then we install the next strand and stress the next strand in that way that both the first strand and the second strand have the same stress. Because if you think about it, if you pull in the second, you somewhat release the first. Then you pull in the third strand, and you can measure the stresses in the first two, and the third strand must have the same stress. So you install the strands in such way that always all already installed strands have the same stress. And you go on and on and on until you have them all in. And the only critical point is the initial stress of the first strand, naturally. Because from that you go down, 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 but that can be determined. And so it's a fairly fail-proof system. You just make sure that all the strands have the same stress. And then you end up with all strands with the same stress. Okay, we have here, looking down, we have here a small winch installed at the tower, which goes up, runs over a reel, and for pulling. That's a little bit closer look. You do not need a tower crane. This little winch is sufficient, which is a cost advantage because a tower crane costs quite some money per day of rental when you have it. So that's why the fabricators stress they only need a little winch. And here now we are at the bottom, and we now prepare the new strand from the reel for pulling in. So first we have to connect it, and we see here this is the so-called shuttle a system where we can connect the new strand to the pull rope inside the PE pipe, which runs up and down like a shuttle. We can also connect two strands, pulling up two at the same time. And then we have here the shuttle, the begin, the pull cable, and from the reel with a very long length, the strand is pulled up into it. That's how it goes on. Now it enters the PE pipe to the tower head. And we see here the temporary connection of the PE pipe, because we have the isolated anchor head. It's not like in a shop fabricated all together, but we have here the collar, you remember, and we have here a come-along, we said on side. A grip hoist is the proper word, ein Greifzug, which with a chain you can pull with a small force which is sufficient to adjust the position here. And the come-along, the grip hoist, is a very important instrument for installing cables. And here we see then one after another is installed. Now, there are various factors influencing the length of the cable. We have to distinguish two basically different methods of cable installation. The one is with completely shop fabricated cables. There we can install by geometry. When we have calculated at this situation we need a shimpack 4-inch, 10 centimeters thick, then that's all you need, because you know you have the correct cable length. And as long as the beam is built correctly and the tower head and all that's very carefully surveyed, you can't go wrong. You must come out with the right structure, because the cable length is predetermined. Now here we do not have a predetermined cable length with side fabricated ones, but we have long strands which we cut off one after another and reinstall. And so there we have to calculate the force, not installation by geometry with the shop fabricated, but installation by force. So we have to calculate carefully for this given situation what force these strands must have. And there are various influences. First of all, the pylon deflects more or less when we install a cable, apply a new force. Then we have to take into account the dead weight of the installation equipment, the derrick, which normally, well, you better weigh it, because otherwise you're always too low. Derricks are always heavier on side than assumed. So you must know that, and there must not be a heap of cement sacks weighing several tons, because that will also change the. You must do good bookkeeping there, and naturally, the sag of the cable changes with the amount of strands you have put in. You start with a rather heavy sag, and later on there's little sag. So all this, of course, can be calculated and is calculated, but for me, who has done several cable stayed bridges with shop fabricated cables given lengths, I always felt better with erection by geometry than with erection by force. But it is done, and of course we can later on change the cable length. We will see once if we are a little bit out. But we need to know exactly the situation during installation from deflection and loads to be able to do it right. There's a little bit more uncertainty, I would call it. Now, the stressing of the individual strands can be done with a so-called monocheck, a check for one strand only, which is a big advantage. Because a mono check, well, this size, a person or two persons can carry. Whereas the check for the full cable weighs 2-3 tons, and you cannot just move it. You need a come-along or a crane or something there. So individual stressing with monojacks, and you see it here, is in a real size. This artisan stresses the last installed individual cable. The same here, small jacks, easily movable, comparatively easily movable. And here now we have the stay cable with all the strands in. What is missing is the special protective pipe at the bottom, which we like to call anti-vandalism pipe, against some people who want to try their pocket knife on them or something on the PE. So normally it's a steel pipe. Underneath the beam we let the strands protrude quite some end, because we want to have the possibility also later on to attach a monocheck and maybe pull it out. We can also, after the initial installation is complete, we can also stress the full cable. Now, for that, then we have to thread all the strands through and anchor it here and use a multi-strand jack, which we can see it here, is a rather heavy thing. It has to be used for the shop fabricated cables all the time, because there we just have the full cable. It's a fact, and it's not easy to move, but we can do it in one go instead of going to each individual strand. Okay, here then we install these bottom pipes, and we can see it here. In this booth there can be a damper, friction damper or rubber damper. I've told you about that in the cable dynamics lecture. And we see the final cable here on top for a steel bridge, final paint, and there's the box. We see it here, and in this box the strands protrude and it's filled with some sort of grease. And so this shall then be good for many years. If we repaint it and so on, there's no reason why the stay cables shall not wear, say, the same 100 years as the bridge is designed for. Cable calculations, I'll do it very brief because in detail it's a little complicated. But the basic idea is that when we have a slack cable and we pull the same amount, say 10 centimeters of cable length, the force is much smaller than when we go on pulling, and the cable becomes nearly taut, nearly straight. Then the same 10 centimeters may mean 4, 5, 6 times the force, and that's what's basically shown here. This is, with a certain initial way, a structural steel member, and the more we stress the rope or the cable, the less slack there is in, the more asymptotically it approaches the elastic bar. It just shows the influence of the sag. Now, at the end of installation, we like to check the cable force. What force do we actually have in the cable? Now, there are 3 possibilities. We can either attach the hydraulic jack again, pull at it, and try to find the moment when the anchor head just lifts off the support. It's a little bit difficult to find out, and then we know from the check gauge, we know the force which is in the cable, direct measurement. Then I just go this way. We can try and survey the cable sag. Now, with a very small calculation, when we know the dead weight of the cable and the length of the cable, then we know the force which corresponds to the sag, just by surveying the sag. And the third is determining the cable eigenfrequencies. Now, the direct measuring with a hydraulic jack can well be done during construction, at the end of construction, when there still is a hydraulic jack and you have a carriage to move it and all these things. Once that's out and construction is complete, it's very expensive to get a jack in there. So not good for the final way. Surveying the cable sag is a little tricky because you have this skew line up there. It can be done. But the easiest method is determining the cable eigenfrequencies. Now again, the basic formula is the cable force depends on the square of the cable length and the square of the first eigenfrequency and the specific weight of the cable. Now, how to measure the eigenfrequency of a cable? That's very simple. I've done it personally quite often. All you do is you get a hemp rope, a washing line, just a little thing. Throw it over the cable 2-3 meters away, and then you start pulling at it. And you find very soon the right frequency from the cable. So you pull at it. One person excites the cable for a big cable stayed bridge easily. You do it until it has something like that amplitude, and then you have a stopwatch and say, now. Then you count 1, 2, 3, 4, 5, 6, up to whatever you like. We've done it up to 100. And then you have the precise cable eigenfrequency, and from that you can calculate the actual cable force. That's the cheapest and simplest method, and it works beautifully. And now the German meticulous people then say, oh, well, yes, this formula assumes a hinged connection and a cable with no bending stiffness. In actual fact, we are fixed and there's no hinge. Okay, if we take that into account, then this little formula gets a little bit more complicated. Still not correct. There is no correct solution, but approximation. In the written script, there is an example shown the differences in cable forces for the various methods. But just remember, the simplest method is excite the cable, measure the eigenfrequencies, and you'll get it. I would say you won't get it by any method better than, say, plus minus 5%. If you're lucky, plus minus 3%. You never get it precise. But as we used to say in the US, that's good enough for bridge work. Okay, thank you very much.